Swayam Prabha. Digital India. Educated India.
So in fact, having shown that B star has is a contraction mapping, it follows from Banach's fixed point theorem that B star has a unique fixed point. So let's call this fixed point V star. Okay, so V star is again a mapping from states to numbers, or equivalently an element of Rn. The fact that it's a fixed point for B star means that B star of V star is V star. Right? This is the definition of being a fixed point. If you write this down now again in long form, right, again invoking the definition of B star, then what we have is that for each element of S, V star of S satisfies being the max overall actions of sum over S prime, T of SAS prime, R of SAS prime plus gamma times V star of S prime. Okay, so this is like a recursive sort of equation. There's V star occurring on the left as well as the right. Now, this looks ominously similar to Bellman's equations, but it's not. Okay. In fact, these are called the Bellman optimality equations. Okay. So, for a given MDP, there is a set of equations like this that are called Bellman optimality equations. So, what is the main difference between this and Bellman equations, right? So, there was a set of Bellman equations for each fixed policy. Okay, and because it was for each policy, we were actually able to get n linear equations in n unknowns. By contrast, there is n equations in n unknowns for each MDP. Okay, Bellman optimality equations are one set of equations for the entire MDP. Okay, they're not for each given policy, but it turns out that these are not linear equations. Okay, so you can see that there's a max operator here. And as soon as you have a max, that means this V star is related non-linearly to this V star. Okay, so we have to solve a non-linear set of equations if we want to get V star. There's multiple families of algorithms for doing this. Okay, this is literally where there is choice available in terms of how we want to go about computing V star. So value iteration, linear programming, and policy iteration are all three different ways that will allow us to get to V star. Okay, and these are the three algorithmic families that we will look into more closely as we go along. Two of them as a part of this week's lecture, and policy iteration next week. Okay, but I mean, why are we interested in calculating V star? Right, I've not told you yet. Well, it's not incidental that we're calling this V star. It turns out that V star, right, which is the unique fixed point of B star, is indeed the value function of any optimal policy for our MDP. Okay, so take any policy pi star, which satisfies pi star being something that looks like what's on the right hand side of the Bellman optimality equations, but which has an argmax instead of the max, right? The action that actually leads to this maximization, let's associate that action with every state, right? If we do that, then such a policy is called pi star. We're going to show, okay, next week, we're not going to take it up this time, that every such policy pi star. Why do I say every such policy? It's because there might be multiple ways in which you can resolve this argmax, right? There might be multiple actions that satisfy that they maximize this quantity over here. So you can pick any action that maximizes and put that inside of your pi star. So there can be multiple possible pi stars. Each of them will be an optimal policy, okay, for the MDP, which means there will be no policy that can strictly exceed the value function of pi star in any state. Okay, that remains a claim at this point of time, but V star is actually going to be the value function of these optimal policies pi star. Okay, which is why we are undertaking different methods to evaluate these policies, right, to somehow compute V star. Okay, again, by way of summary, we came up to the point saying that V star is a contraction mapping with contraction factor gamma. it is going to operate on a Banach space, and therefore it followed that it must have a unique fixed point. We're going to call that unique fixed point V star, and suddenly there is a lot of light being thrown on V star, right? We're interested in V star. Why is that interest? Why are there three different families of algorithms that are trying to compute V star? It's because V star is special, right? For an MDP, we have claimed, we've not shown this yet, there are optimal policies, right? V star, right, which is the unique fixed point of V star, is actually the value function of these optimal policies, okay? And therefore, we are pursuing through multiple channels, right, the computation of V star. Okay, so that's what's coming up next. So what we'll do right after is the first family of algorithms, which is called value iteration. Thereafter, we will follow up with linear programming, okay, a different approach to get to V star and through that also to pi star. Okay, so here's value iteration. It actually does not need too much more than what we've already seen. Okay, so we've already seen that V star is the unique fixed point of V star, right? So the most natural way to get to V star is the iterative approach. So what we do is we start with any arbitrary value function type object, right? Or element of R to the n, V0. Okay, you start with V0, apply B star to that. Okay, you'll get V1. Apply B star to that, you'll get V2. You keep doing this. Okay, we know that if you do it an infinite number of times, what you'll eventually have is V star. Right? Doing that precisely is the value iteration algorithm. If you want, you can write it down as longer form pseudocode. So we're starting out with any arbitrary sort of, let's say, initialization of our optimal value function. We don't know what it is. So we start with a guess of your optimal value function, call it V0. And then you keep doing this. Okay, what do? You set Vt plus 1 of S for each S to be max over A, sum over S prime, T of SA, S prime, R of SA, S prime plus gamma times Vt of S prime. Okay, you take your previous iterate. Essentially, what we are doing is applying the Bellman optimality operator, right, which calculates a vector, right? Therefore, in terms of pseudocode, you need to do one update for each element of this vector. So by doing that, you go from Vt to Vt plus 1. In practice, you can't do anything an infinite number of times. Okay. So in practice, what you will do is when you find that Vt and Vt minus 1 are close enough to each other, right? Then you'll stop. Okay, so in practice, what might happen is you might only have 32 bits or 64 bits of representation on your machine, right? So beyond a point, you might not be able to differentiate Vt and Vt minus 1, right? Or you might just say, I'll set some small epsilon, right? Maybe 10 power minus 10 or something like that. And say that if each element of Vt is within 10 power minus 10 of each element of the corresponding element of Vt minus 1, I'm good to stop. Okay. I mean, in theory, this is an approximation. In practice, this is okay, right? Because that's all the representation power you have on your machine. Having stopped at Vt, right? When this condition got satisfied, you'll basically act as though the Vt that you have is V star. Okay, even though in theory it's not, in practice it's close enough to V star, so we just think of it as V star. So this method is maybe the most straightforward thing to do, right? Because we know that V star is a fixed point of B star. You just apply B star as long as you can, and when you can't really proceed further, given the number of bits you have, you stop, and that's your answer. It's easy, right? You can see that you can write like 5 lines of pseudocode and be done with it. It's quick to implement. It works reasonably well in practice. Okay, so this is one way of calculating V star. But before going further, what I need to, I think, give you some clarity on is it actually suffices to know V star. Okay, remember that the original problem we wanted to solve was calculating an optimal policy pi star. So what I'm going to show you here is that once you have V star, right, getting Q star, pi star is relatively easy. Okay, so you should really think of these three quantities, V star, Q star, and pi star, as more or less interchangeable. Of course, it is hard to get to any one of them, but once you have any one of them, you can get the others. So how does that happen? So let's say our MDP is S, A, T, R, and gamma, and we have V star. Okay, so maybe we got V star by value iteration. Can we now get Q star? Most certainly you can, right? Just invoke the definition of Q star. It's going to be the expected long-term reward of taking action A for the first time step, and thereafter acting according to an optimal policy, right? So that will give you V star of S prime. And so you can calculate Q star of S prime, Q star of SA for every state and action by just writing this out. If you have Q star, can you then get pi star? Again, yes. So the simple way of saying this is that pi star is the policy that is greedy with respect to Q star. Okay, modulo tie breaking. So when you're in a particular state, look at the Q star values for all the actions. Whichever action maximizes Q star, right? Just take that action. Okay, if there's multiple, you can resolve this tie in different ways. But whichever way you do it, right, you can call that policy pi star. And if you have pi star, can we get back V star? Turns out there's actually a simple way of doing it. You just do policy evaluation, right? We know that V star is the value function of optimal policy pi star. Right? So if you all solve the Bellman equations for pi star, you have V star. Right? So from V star you can get Q star, from Q star you can get pi star, from pi star you can get V star. So basically you can get any of these from the others in a relatively straightforward way. So what we've seen, right, is one planning algorithm value iteration that gave us V star, right? But this should satisfy you in the sense that once we have the V star, it's a relatively simple matter extracting pi star from that. Okay, so there you go. Value iteration is one way of getting to your optimal policy. The minor caveat is that in theory, right, if you do value iteration for a finite number of iterations, that's a close enough approximation of V star. It's not exactly V star. Okay, in general, it need not be. But up to machine precision and as an algorithm for practical application, value iteration works just fine. Okay, so there you go. What's coming up next is a second family of algorithms for MDP planning. And this goes through the approach of what's called linear programming. Okay, so let's look at that next. So just to be clear about it, linear programming is an independent topic in operations research. It's been studied for very long, right? Again, maybe starting from 1940s and 50s. What we're going to do is to translate the MDP planning problem into a linear programming problem, okay? And just piggyback on existing approaches for solving linear programming, okay? Just given the prominence it has, people have looked at it, right? There are many very efficient ways of solving linear programs. And so the effort that I'm going to describe to you is that of taking the MDP planning problem and translating it into what's called a linear programming problem. So to begin, we will just give like a brief review of linear programming. I hope that you have encountered linear programming or LP in the past as a part of maybe an algorithms course or a course in linear optimization. So maybe you have, maybe you haven't, right? So this 5 minutes will just give you the big picture, but I very strongly encourage the student to follow up, try and understand linear programming if you haven't done it before. Okay, it's really very useful for every student of science and engineering to know. Okay, so what is linear programming? The problem is this. So we have, let's say, m real valued variables, x1 through xm. What we would like to do is to optimize a linear function of these variables. Okay, something like alpha 1 times x1 plus alpha 2 times x2, etc. But also for the value that we find, right, the solution that we find, not only to optimize this linear function, but to also satisfy certain constraints which are also linear in these same variables. Okay, so I mean, rather than say all this in English, it's good to look at an example. So for example, here is a linear program. Okay, it's a simple linear program with two variables, x1 and x2. What we would like to do is maximize x1 plus 2x2. Okay, that's a linear function of x1 and x2, subject to satisfying three constraints, c1, c2, and c3, which are all linear. okay, subject to the constraints that x1 plus x2 does not exceed 9, 4x1 minus 13x2 less than or equal to minus 75, right? And x1 is less than or equal to 5. You can have more constraints, fewer constraints, but these constraints must also be linear. Okay, so it's not okay to have x1 squared showing up here, right, or square root of x2, something like that. It must just, each of these constraints must be of the form ax1 plus bx2 less than or equal to some c. Okay, I mean, if you have greater than or equal to, right, then you can make that a less than or equal to by multiplying by minus 1, right? So that is still going to keep it linear. So problems like this, right, are very, very like commonly encountered in various fields of engineering. Various mathematical problems, right, can be described using this linear programming formulation. So it's a very well studied problem, and also to say that given the attention it has received, there are very, very good solvers for linear programs. So what do I mean by that? You can give this linear program, let's say, as an input to a solver, right? And it has to give you the output. It will find you the x1 and x2 that maximize these things, this objective function subject to these constraints. Okay, it will do it very quickly. Even if you have like millions of variables, right? For somewhat naturally occurring problems, there are very efficient solvers, right? Both commercial ones and ones that you can sort of download and use for free, right? Which are open source, in fact. Okay, so we will not be getting into the solvers, really how linear programming, really how linear programs are solved. We are just going to use the fact that if we translate, right, our given problem into a problem that looks like this, right, maximization of an objective function subject to constraints, both of which are linear, then we can quickly derive the answer out of that. Right? That's really the strategy that we are going to adopt. I'm going to maybe just give you a very, very brief idea about how linear programs are solved. We are not going to get into the whole technicality, right, the sophisticated ways of doing it, but conceptually, right, this is just to build some intuition for you. So this is the linear program from the previous slide. We have to maximize this linear function subject to these constraints. So first step, right, let us look at these constraints. Okay, so what it means to satisfy linear constraints means, if you look at it as a picture, we want to find an x1 and an x2. Each of these constraints looks like drawing a line, right, and saying that our x1 and x2 can only lie to one side of the line. Right? So take, for example, C1. C1 says that x1 plus x2 must be less than or equal to 9. Right? So this line over here is actually the line x1 plus x2 is equal to 9. And if you have a less than or equal to, it means we're only interested in points that lie to one side of the line. Okay. Similarly for C2, C3, right? C3 says x1 is less than or equal to 5. That's easy to see, right? You can only look at points that are to the left of this line. Now, it's not very hard to see that if at all, right, there is a feasible set, right? If there are points which satisfy all your constraints, those points are set to lie in what is called your feasible set. It might not exist, right? There might be constraints which conflict with each other. There might be no feasible set, but if there is a feasible set, it's going to be convex. Okay, that is simply like a consequence of the fact that these are all linear constraints. Okay, so given a linear program, maybe the first step is to see what the feasible set is. Once you have your feasible set, you ask which points inside of my feasible set maximize my objective function. So that again has a nice geometric interpretation. So remember, the objective function here is x1 plus 2 times x2, right? So in some sense, for a given point x1, x2, right, the value of its objective function is given by just taking a dot product with the vector 1, 2, right? So 1, 2 looks like this. Okay, this is the 1, 2 vector. Now, you take any line, or in general hyperplane, okay, in higher dimensions, that is perpendicular to this vector 1, 2. That is the set of all points that have basically the same value of the objective function. Okay, so for example, this line over here, if you look at, right, the claim is every point on this line has the same value of the objective function. Okay, that's because the value of the objective function is simply the dot product with this 1, 2 vector, right? This is something that you can mathematically verify if you want. Okay, but as you then move this hyperplane in the direction of the vector, right, either front or back, you're going to again get equally good or bad points. How good or bad depends on how far you have pushed it this way or that. Okay, so as you push it in the direction that 1, 2 is going, you're going to get sets of points with equal objective function, but that objective getting better and better and better. Okay? If you move it in the other direction, it's going to get worse and worse and worse. So literally the best you can do by pushing out the point, if you want the points to be inside of this feasible set, is what you will get by moving your plane out to this vertex over here, okay, in our example. Okay, and at that point, you have to stop and say, well, this intersection, what's happening at this vertex over here is the best I can do, right? It is the x1, x2 that lies inside the feasible set, but still maximizes this objective function. Okay, so it's not always the case that you will get a single point. I mean, depending on the actual configuration of the problem, sometimes you might get a line, right, or a hyperplane that's a subset of your the convex polytope that results from this. Okay, unless you take extra caution, right, very often you will find that it is a single point. Okay, so what I have told you here is that when you think of solving a linear program, conceptually at least, the first step is to ask what is the set of feasible points, and the next step is to look for that feasible point which has the highest objective function, and that is done quite easily by looking at the vector, right, representing the objective function, and then pushing as far out as you can in the direction of that vector, but still intersecting the feasible set. See, actual solvers might not do step 1 and step 2 completely, right? So, I mean, if you have, I don't know, D constraints, then the actual feasible set, right, the convex polytope that results from that can have like an exponential number of phases. Okay, so the algorithm actually will not be doing it by identifying the feasible set first and then finding the maximizing point. It might do the two of these things together, okay, in a more efficient way. But yeah, conceptually, this is how it proceeds. Okay, so now you have some intuition about how a linear program is, right? What really the game is to try and solve a linear program. Let's now get back to our reason for looking at linear programs, which is basically we want to find V star, right, or pi star. So let's start with what we already know, Bellman optimality equations, which I have written down here again. V star of S, right, for each state S equals max over actions T of SA S prime, R of SA S prime plus gamma times V star of S prime. Okay, the issue we have is that these are non-linear equations, okay, but we want to do linear programming. So how do we do it? So first thing we have to do is decide what our variables are going to be, right? It was x1 and x2 in our examples, but if we want to do this for our MDP, right, what are our variables going to be? So looking at Bellman optimality equations, the most natural choice of variables is to have one value, right, for each state. Right, so you want to have V of S1, V of S2, V of Sn, with the hope that you will somehow involve these in an LP. Okay, you'll put linear constraints on them. You'll set up a linear objective function so that the solution to that LP will actually be V star. Okay, that is the direction in which we are proceeding. So we will go with this choice of having n variables. Let's just denote them V S1 through V Sm. Okay, what we need to do now is to subject them to linear constraints and come up with a linear objective function, along with the guarantee that the solution to that linear program will be V star. Okay, so how do we do that? So first thing is, although Bellman optimality equations are non-linear because of the max operator, you can linearize them by just invoking the definition of max, right? When you say x is max of yz, right? So it actually is true that this means that x is greater than or equal to y, x is also greater than or equal to z, right? It will actually be exactly equal to one of them, but it certainly is the case that it is greater than or equal to everything inside of the set we are maximizing over, right? So we can simply say that for each S, right? V of S has to be greater than or equal to T of S A S prime, R of S A S prime plus gamma of B of S prime summed over S prime. But for every action A, okay, here we're doing a maximizing over A. So we are just going to replace that max by saying, let's write out every single action, right? B of S has to be greater than or equal to the corresponding right hand side.